All right, this is Chapter 4, Section 4, the Fundamental Theorem of Calculus. So, we're just going to dive straight in. The Fundamental Theorem of Calculus says if a function f is continuous on the closed interval a to b, and capital F is an antiderivative of lowercase f on the interval a to b, then the definite integral from a to b of f of x dx equals f of b minus f of a. So basically we take the antiderivative, we plug in the upper bound of integration, minus plugging in the lower bound of integration. Some guidelines here. If provided you can find an antiderivative of f, we now have a way to evaluate a definite integral without having to use the limit of a sum. Much, much shorter than what we were doing before. When applying the fundamental theorem of calculus, the notation shown here is pretty helpful. It's what you basically use. We use a little bracket type thing, or sometimes we just use a straight line. We put those integration bounds after that antiderivative. So to evaluate 1 to 3 of x cubed dx, we would write it like this, and then we'd take the antiderivative of x cubed is x to the 4th power over 4 from 1 to 3. Plug in 3 minus plug in 1, we got 20 there. And the third guideline here, it's not necessary to include a constant of integration in the antiderivative. If you look through all of this, you'll see that these constants of integration cancel out, so they are pointless. So let's try some examples. For part A here, we have the definite integral from 1 to 2 of x squared minus 3 dx. We start with an antiderivative of x squared minus 3. Remember that we add 1 to the exponent, divide by the new exponent, and 3 gives me 3x. If it's two terms, we usually put it in brackets. Our bounds of integration go on the end of the second bracket. So now we plug in 2. So we have 2 cubed over 3 minus 3 times 2 minus, plug in the lower bound of integration, 1 cubed over 3 minus 3 times 1. And now we just do the math. 2 cubed is 8 over 3 minus 6 minus 1/3 minus 3. So I have 8/3 minus 6, 8 minus 18/3, that's negative 10/3, minus 1/3 minus 3, 3 is 9/3, so I have negative 8/3, minus the negative is plus positive, so I get negative 2/3 for my answer. Next up we have the integral from 1 to 4 of 3 square root of x dx. Well, remember that a constant can be pulled out front of an integral, and the square root of x is x to the 1/2 power dx. So now we can take our antiderivative. 3 times, we add 1 to our power, so it's x to the 3/2, and divide by that new power, and that goes from 1 to 4. I would clean this up a little. The 3 could be inside or outside. It doesn't make a difference. So my 3/2, if I'm dividing by 3/2, I'm really multiplying by 2/3, x to the 3/2 power from 1 to 4. And those 3's cancel, leaving me 2x to the 3/2 power from 1 to 4. And now we plug in our values. Plug in the top bound first, so 2 times 4 to the 3/2 power, minus 2 times 1 to the 3/2 power. 4 to the 3/2 power, that's 4 square root, the square root of 4, which is 2. 2 cubed is 8 times 2 again, which is 16. 1 to any power is just 1. So 2 times 1 is 2. And so we get 14 for that definite integral. And our third one here, we have the integral from 0 to pi over 2, or pi over 4, of secant squared x dx. Well, now we have to remember secant squared is secant squared's antiderivative is tangent of x from 0 to pi over 4. Remember that the derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. So we take the tangent of pi over 4 minus the tangent of 0. The tangent of pi over 4 is 1. The tangent of 0 is 0, giving me 1 as my final answer. So now we're going to look at an absolute value problem. When it comes to an absolute value problem, it helps to think about the graph. The graph of the absolute value of 2x minus 1. Well, an absolute value graph is usually, or always, a V. We shift it 1 to the right, so our vertex is at 1, 0. The slope of each side is 2, or negative 2. So 2, 2, or 2, 2. So there's our function. We are finding the integral from 0 to 2. Well, we have two different pieces there. We actually need to break it apart. We're going to break it apart at 0 to 1 and 1 to 2. 1 to 2, we have a positive slope, so that's just 2x minus 1 dx. 0 to 2, though, we have that other side of it. That is a negative slope. So it's just the opposite of the entire equation, dx. And then we add the 2 together. So I would distribute that negative. And now we take two separate antiderivatives. The antiderivative of negative 2x plus 1 is negative 2x squared divided by 2 plus x from 0 to 1. Plus the antiderivative of 2x minus 1 is 2x squared divided by 2 minus x from 1 to 2. Now I realize that this simplifies a little, but my 2's cancel, and my 2's cancel. All right, we plug in our upper bound, so 1. So we have negative 1 squared plus 1 minus, plug in 0, I get negative 0 plus 0. Plus, for the second one, we plug in 2 first. 2 squared is 4 minus 2 minus, plug in 1. 1 squared is 1 minus 1. And there we go. We get a 0 minus 0 plus 2 minus 0. So we get an area of 2. Now let's find the area of the region bounded by the graph of this function, the x-axis, and the vertical lines x equals 0 and x equals 2. That is a fancy way of saying find the definite integral from 0 to 2 of this function dx. So we start with the antiderivative. Well, 2x squared becomes x cubed over 3 with a 2 in there still, minus 3x squared divided by 2 plus 2x evaluated from 0 to 2. And then we plug in 2. So we have 2 times 2 cubed over 3 minus 3 times 2 squared over 2 plus 2 times 2 minus 2 times 0 cubed over 3 minus 3 times 0 squared over 2 plus 2 times 0. That whole side is 0. So we have 2 times 8, which is 16 over 3, minus 3 times 4, which is 12 over 2, plus 4, minus 0. And so I have 16 over 3 minus 6 plus 4, which is 16 thirds minus 2, which is 10 thirds for our final area. All right, we are also going to talk about something called the mean value theorem for integrals. The mean value theorem for integrals just tells us that in any closed interval, there's a number c such that the integral from a to b of f of x dx is equal to f of c times b minus a. So basically that means there is a value of c somewhere in this integral or interval that if I make a rectangle between my two bounds at that height, wherever c is, whatever height that is, this rectangle has the same area as that curve did. That's all it says. It doesn't say how to find that, just says it exists. We also have the average value of a function. Now this one is very important. If f is integrable on the closed interval a to b, then the average value of the function is 1 over b minus a, right, my interval, times the sum from a to b of f of x dx. So we take 1 over the difference times the integral. So let's find the average value of f of x equals 3x squared minus 2x on the interval 1 to 4. We start with 1 over 4 minus 1 times the integral from 1 to 4 of our function, which is 3x squared minus 2x dx. So we have 1/3 times the antiderivative is x cubed minus x squared from 1 to 4. So I have 1/3 times, let's plug in 4. 4 cubed is 64, minus 4 squared is 16, minus, let's plug in 1. 1 cubed is 1, minus 1 squared is 1. So that's 1/3 of 64 minus 16, which is 48, minus 0. So really I have 1/3 of 48, which is 16. The average value of that function is 16. And now for a big, long problem here. At different altitudes in the Earth's atmosphere, sound travels at different speeds. The speed of sound, s of x, in meters per second, can be modeled by this crazy piecewise function, where x is the altitude in kilometers. This problem asks for the average speed of sound over the interval 0 to 80. All right, hold on, because this problem's going to get crazy. So we start off with 1 over b minus a. Well, in this case, b is 80, and a is 0, times the integral from 0 to 80 of s of x dx. Well, the problem here is that s of x is piecewise, which just means that our integral is going to be in pieces. So I have 1 over 80 times the integral from 0 to 11.5 of the first piece, which is negative 4x plus 341 dx, plus the second piece, which is 11.5 to 22 of 295 dx, plus the third piece, which is 22 to 32 of 3/4 x plus 278.5 dx, plus the next piece, which is 32 to 50, 3/2 x plus 254.5 dx. And I gotta go on another line, the last piece, which is 50 to 80, negative 3/2 x plus 404.5 dx. All right, a whole lot to do here. So we are definitely going to rely on our calculators in a little bit. So I have 1/80 times the antiderivative of negative 4x plus 341, which is negative 2x squared plus 341x from 0 to 11.5. Plus the antiderivative of 295 dx is 295x from 11.5 to 22. The antiderivative of 3/4 x plus 278.5 is 3x squared over 8 plus 278.5x from 22 to 32. Plus the antiderivative of this part here, 3/2 x plus 254.5, is 3/4 x squared plus 254.5x from 32 to 50. And our final piece here, the antiderivative of negative 3/2 x plus 404.5 is negative 3/4 x squared plus 404.5x from 50 to 80. All right, let's rely on our calculator now. Let's take negative 2 times 11.5 squared plus 341 times 11.5 minus negative 2 times 0 squared plus 341 times 0. And I know what you're thinking, Miss Dupree, that second part is just 0. Correct. We get 3657. So 1/80th, 3657. That was my first integral. Second one, 295x. We take 295 times 22 minus 295 times 11.5, 3097.5. Our third piece here, I'm going to take 3/8 times 32 squared plus 278.5 times 32 minus 3/8 times 22 squared plus 278.5 times 22. 2,987.5. Third piece, 3/4 x squared plus 254.5x. I take 3/4 times 50 squared plus 254.5 times 50 minus 3/4 times 32 squared plus 254.5 times 32. Please notice that in that second piece of it, I am definitely putting parentheses around it because I am subtracting the whole thing, which means I would have to distribute the subtraction. If you do not put those parentheses, you will not get the correct answer. And for my third one, or my last one here, I have negative 3/4 times 80 squared plus 404.5 times 80 minus negative 3/4 times 50 squared plus 404.5 times 50. I get 9,210. And now I just add these all up. 3657 plus 3,097.5 plus 2987.5 plus 5688 plus 9210. I have 1/80th times 24,640. And when I get that, it is an average value of 308 meters per second.